Hola, here is my response to the assessment to develop a model can accurately forecast energy production based on ambient environmental conditions. Are working with a dataset of 9,568 hourly readings, which includes 4 key input features and 1 target variable. My modeling approach. Because of the historical dataset, this is a regression problem, as I'm predicting a continuous value, the electrical energy output. Our input features are temperature, ambient pressure, relative humidity, and exhaust vacuum. These environmental factors all play a role in determining energy production. For my analysis, I considered a couple of algorithms: linear regression as a baseline, random forest regression for its ability to capture nonlinear relationships, and gradient boosting for its typically high performance. I saw that each method has different strengths, so I coded a Python program to simulate the ML for both methods. How did I build my models? I split our data into 3 sets: 70% for training, 15% for validation, and 15% for testing. This split allows me to train our models, fine-tune them, and then evaluate their performance on unseen data. I used 5-fold cross-validation during our model comparison phase. This technique helps ensure our results are robust and not overly influenced by any particular data split. I focused on comparing 2 main models, linear regression and random forest regression. For the random forest model, I performed hyperparameter tuning, adjusting factors like the number of trees and the maximum depth of each tree. As in the course, this process helped me find the optimal configuration for our specific dataset. I chose root mean squared error, RMSE, as my primary metric. RMSE gives me an idea of how far off our predictions are, on average, in the same units as our target variable.
My program plotted the correlation matrix using the scikit-learn library recommended in the course. This visualization helps me understand the relationships between our features and the target variable, just as we saw in the course. The picture shows that temperature and exhaust vacuum strongly correlate with energy output. When I compared our models using the validation set, I found that the random forest model outperformed linear regression. The random forest achieved a low RMSE, indicating more accurate predictions. This is likely due to random forest's ability to capture complex, nonlinear relationships in the data. My program also plotted the actual underscore versus underscore predicted, PNG, showing our random forest model's actual versus predicted values. The closer the points are to the diagonal line, the more accurate our predictions. The picture shows how my model performs well across the range of energy output values, with most predictions falling close to the actual values, as we can see from the actual versus. Predicted plot, the random forest model performs well across the range of energy output values, with most predictions falling close to the diagonal line, indicating a strong correlation between predicted and actual values. The final RMSE on our test set was approximately 3.24 MW, which indicates strong predictive performance. Regarding feature importance, I found that temperature, AT, and exhaust vacuum, V, had the strongest influence on our predictions. This aligns with our earlier correlation analysis, where we observed that temperature had a very strong negative correlation, minus 0.95, with the net hourly electrical energy output, while exhaust vacuum also showed a strong negative correlation, minus 0.87.